Alright, so you want to be a programmer. Alright, cool. I will first bombard you with a lot of terminology, but that's intentional. You don't have to memorize everything. Just go with it. It does not matter which programming language you want to learn. All programming languages are about writing instructions and handling data. That is the essence of programming. The instructions are called source code in the case of software. You write source code in a file, and that becomes your software application. Processors do not understand human-friendly languages. They read instructions called machine code, made up of bits, zeros and ones. A bit is the smallest unit of data and can represent a 0 or 1, also known as a boolean. These instructions form what is known as machine language. This is the first generation programming language. Every processor has its own unique set of machine instructions, which is why there are multiple machine languages. To simplify machine language, assembly language was invented. It assigns a human-readable name or command to each machine instruction. Assembly languages are classified as second-generation programming languages. Even assembly was not user-friendly enough. That led to the development of high programming languages. Languages that more closely resemble English and are easier to write and understand. Languages such as C, COBOL, Fortran, Java, and Pascal fall into this category. Processors do not understand these languages directly. They must either be translated into machine code by a software application or executed step by step by another software application. The former is called a compiler, and the latter is called an interpreter. These tools allow you to create a factory of your own. In the manufacturing industry, a factory is all about instructions and handling materials, the equivalent of data in software. For example, to create a factory that produces a drink, you need to know how the drink is made. You need a list of ingredients and a process for handling them. The ingredients represent the data, and the instructions represent how the data is processed. These instructions are referred to as business logic. The ingredients are delivered in packages. In programming, we use variables to store data, similar to how ingredients are delivered in different kinds of packages. For example, sugar might come in a bag and sugar cubes in a box. Likewise, in programming, variables come in different data types depending on the kind of data they hold. Programming languages that require you to explicitly define the type of a variable are considered strongly typed. These are often used to control hardware and contain primitive types like integers and booleans. Primitive types are the most basic building blocks of data. They are often numbers, but also include booleans, which are just bits, and characters, which are stored as numbers too. For example, in Java and JavaScript, characters and strings are stored as arrays of numbers, often using 16-bit encodings. Computers only understand numbers, particularly integers. In most programming languages, an integer typically consists of 32 bits. Text on your computer consists of an array of bytes. Each byte is mapped to a character, digit, punctuation mark, and so on. Programming languages that do not require variable types to be declared are considered weakly typed. These are never designed to control hardware, but rather to control other software such as operating systems, databases, browsers, and so on. An operating system or OS is the main software layer above the hardware. It manages resources and provides services to applications. For instance, a music player application does not interact directly with the audio hardware. It uses drivers provided by the OS. Each OS has its own drivers and components, just as each house contains different furniture. This complicates software development across platforms. One solution is to reuse existing source code and adjust it to run on another OS. In general, you will not need to modify the source code significantly. Unless your source code interacts with specific hardware or OS features, it is mostly a matter of using the appropriate compiler. Another solution is to use a language that relies on an interpreter already compiled to run on the OSs you want to support. This approach enables cross-platform compatibility. In the past, OSs ran only one software application at a time, so programming languages did not need to be complex. This led to procedural programming, where instructions are grouped into procedures. Early user interaction was through CLIs or command line interfaces, text-based input systems. A procedure might check whether a discount applies to a product and, if so, subtract it from the price. Here, the price is the data, and the instructions are the logic that evaluates and adjusts it. Procedural programming is still in use today. The SQL programming language, yes, that is really how it is pronounced, is often used procedurally in database systems that support stored procedures, but its core is declarative. That means you describe what you want to happen, and the system figures out how to do it. You will learn more about declarative versus procedural languages later in this series. As computers grew more complex, graphical user interfaces or GUIs replaced the command line. GUIs allowed users to interact with graphical elements like icons and windows, requiring more processing power and memory. To manage this complexity, Object-Oriented Programming or OOP was introduced. OOP lets you create objects, which are like mini programs. They have methods, And fields. Objects are initialized, not called like procedures. This means an object must be stored in a variable before it can be used. Objects are considered instances of user-defined data types, called classes. While primitive types represent basic values like numbers or booleans, objects represent more complex data structures. To build real-world software, you must define domains, the entities your program interacts with. For example, a warehouse sells products. You can define a class for a product. Classes can be inherited. For example, shoes, pants, and sweaters can extend the product class. If a class is useful only as a template and does not need to be initialized directly, it is called an interface. By defining a product interface, you can create classes such as shoes, pants, and sweaters that conform to the interface. These classes represent domains. In the product interface, you define properties such as ID, name, price, and so on. In a database, a similar process occurs. A relational database management system or RDBMS consists out of tables. A table is a blueprint for organizing data. It is similar to a domain in software engineering, but in data engineering, table focuses on what data needs to be stored. For example, in the shoes domain, you define the type of data that describes a shoe. In a table, only the data structure is defined, not the business logic. Just as in programming, data types must be defined for each field in a table. When a class is initialized, the data it holds is stored temporarily in the computer's memory. This is referred to as data volatility or data transience. In contrast, data stored in the database is saved permanently unless deleted intentionally. This is called data persistence. When writing software that communicates with the database, you must define classes to retrieve and manipulate data. These classes are called data access objects or DAOs. For instance, you can define a DAO for products to perform create, read, update, and delete operations. These are collectively known as CRUD, which is what SQL is designed for. Data creation usually involves all parties in a software application. For example, a store provides data about its products, and a user provides personal data to create an account. Reading is about manipulating and displaying data, especially to a GUI. The part of the application the user interacts with is called the front end. Everything else is the back end, particularly in web applications delivered to a user's browser from a server. A server is a computer just like the user's device. To manage both the front end and the back end, developers often use a software design pattern. One popular pattern is MVC or Model View Controller. The model manages the data, the view handles how the data is presented, and the controller contains the business logic that connects the two. Each of these components involves data and instructions. Even with the best practices, source code is not always easy to understand, especially for programmers who did not write it. Business-specific terminology can also create confusion. This is why good documentation is essential. Most languages support comments, non-executable lines of text to explain the code to other developers. These comments allow documentation to be embedded directly into code. Software engineering is still a relatively new profession. It was originally modeled after civil engineering, which inspired terms like software engineering. Civil engineering often uses the waterfall methodology, a structured, linear process. But most modern software needs to be developed iteratively, incrementally, or both. Software engineering has matured and deserves to be treated as its own profession. Unfortunately, the software industry is often controlled by non-technical managers. They are sold methodologies like Agile, not because they work, but because they sound good. The Agile Manifesto says that working software is more important than documentation. But ironically, you need documentation to understand Agile. Popular Agile frameworks include Scrum, Kanban, and Extreme Programming. Avoid them whenever possible. Scrum, in particular, is considered so effective that every company I've seen using it has had to customize it in an attempt to make it functional. Many companies adopt software frameworks to reduce cost and complexity, but this often means developers never learn real software engineering. I teach professional, straight-to-the-point software engineering on this channel. I've more than a quarter of a century of experience in software engineering. I've seen it all, I've done it all. If you are looking to learn real software engineering, you are in the right place. I am trying to record, but for some reason there are airplanes all over the place above my house. Super annoying.